Good evening, everybody. I hope you're all fine. We are starting our first lesson today under this topic, which is binomial expansion. And we'll start by looking at what binomial expansion really is. So, binomial expansion is the process of expanding an expression of the form open brackets a plus b close brackets to the power n using binomial theorem. That's just about the definition of binomial expansion. But before we could go further, it's very important for us to discuss few things, like things to do with what is Pascal's triangle, factorial notation, before we proceed to binomial theorem. So Pascal's triangle is it's a triangular arrangement of numbers in which each number is the sum of the two numbers directly above it. So it starts like Pascal's triangle starts like this. You have a 1 there, and then you have a 1 in the second row, and then you happen to have, you put ones at the end first, and then these two numbers here, you now add them. This number in that number, to give you a 2, you add them, you have a 2, and then you move to this, you also put ones at the end. After that, you start adding the top numbers. 1 plus 2, you get a 3, and then 2 plus 1, you also get a 3. And then when we are looking for the power of 4, you put ones at the end, and then you start 1 plus 3, you get a 4, and then 3 plus 3, you get a 6, and 3 plus 1, you get a 4. So these are just coefficients. These are just coefficients that we use in our expansion. Let's say, for example, if we want to expand, let's say we want to expand a plus b to the power 2 like this. So in order for us to expand this to the power 2, we are going to have 2 choose 0, and then a to the power 2, b to the power 0, plus 2 choose 1, a to the power 2 minus 1, which is 1, and then b to the power 1, and then plus 2 to the power 2, and then we're going to have a to the power 2 minus 2, which is 0, and b to the power 2. So Pascal's triangle is only giving us the coefficient, what should be here, what should be there, and what should be there. So when you look at this, since the highest power is 2, you go to Pascal's triangle, where is 2? So 2, the power of 2, you have to find the 2 there. The power of 3, you're going to have a 3. 4, you have a 4 there. So this 2, it comes in the third row. 1, 2, 3, that's why you find 2. So for the first piece, 2 choose 0, the answer is 1. That's what that one that you have the coefficient. So here it's 1, and then the coefficient, this part here, 2 choose 1, the answer is 2. That's what we have there, and then 1. So Pascal's triangle only gives us the coefficients. Pascal's triangle only gives us the coefficients. So that's about Pascal's triangle. So there's nothing much to talk about under that. We move to the second part. The second part is the factorial. The second part is about, or before we move to that part, the second part is the factorial notation. So factorial notation is as follows. You have, let's say you have n factorial. This is what it means, n factorial, and this is equals to, you expand this n up to 1, so it will be n The next term is going to be n. It will be reducing by 1. like this, and then the next term it will be n minus 2, and then it will continue like that up to the point where you reach 1. So it will be 3 times 2 times 1. That's when it will end. That's about factorial. So if you are given, let's say 5 factorial, 5 factorial is simply equals to 5. 5 minus 1 is 4. So it will be 5 times 4 times 3 times 2 times 1. When you reach at 1, that's 1 is the last value that you have when you're expanding the factorial like that. So in your expansion, you can end somewhere. For example, if I write 6 factorial here, I can just say 6 times 5. If I want to end at 5, I'll just put a factorial like that. It's one and the same. So 6 factorial is the same as 6 times 5 factorial. Or you can say 6 factorial is the same as 6 times 5 times 4 times, you can end even at 3 there and put a factorial like this. So you can expand it in that manner. So that's about the factorial notation. So we move to binomial coefficients. Binomial coefficients. For example, if you happen to have, let's say n combination r like that. So this is read as n choose r. So the expansion of this is as follows. This n here is a positive integer. Even r is a positive integer, and n is always greater than this part which is here. So the expansion of this is n factorial over r factorial. Then next, open brackets, the top part which is n minus the down part which is r factorial like that. So these are coefficients. These are just coefficients. So in case maybe someone gives you to say 4 choose 2, find the value of this part here, you just follow the same procedure. It is 4 factorial divided by 2 factorial. Next, you subtract 4 minus 2, which is equals to, say, 4 minus 2 factorial, and then this is going to be 4 factorial over 2 factorial. 4 minus 2 is 2 factorial. So this part you can expand this. You can find the actual value of 4 factorial, 2 factorial, and this. Or if you want, since you have 2 factorial underneath, you can just say 4 times 3 times 2. When you reach at 2 there, you can just put a factorial, so that this other 2 factorial cancels with this 2 factorial which is in the denominator. So this factorial here and this factorial cancels, and then you end up with 4 times 3, which is 12, over 2 factorial. 2 factorial is equals to 2 times 1, which is 2. So the answer here is equals to, 6. That's what we have. Only 4 choose 2. But if at all you want, there is no loss of generality in one simplifying 4 factorial. Say it's 4 times 3 times 2 times 1 over 2 factorial is 2 times 1, and then the other 2 factorial is 2 times 1. So already here, 4 times 3 is 12. 12 times 2 is 24. Multiplied by 1, you have 24 here, over 2 times 1 is 2. 2 times 2 is 4 times 1 is 4. So you have 24 divided by 4, which will still give us what? 6. So there is no loss of generality in one. Expanding this up to the end, expanding the down part up to the end, is still fine. That's about that part which is there.